Let us begin with the mathematical calculations. We have a displacement u vector. We have two in the two-dimensional case. We have u1 and u2, and then we take the total differentiation, and then du equal to partial u partial x time dx. Okay. And then this partial u partial x can be expressed as a matrix, okay? And this dx vector can be expressed as a vector, okay? So if somebody asks you what is the meaning of partial u partial x, you just say that this is a matrix, okay? Partial u partial x, partial u1 partial x1, partial u1 partial x2, so on and so forth. And let me explain to you what we can have mathematically by having this relation. Okay, we have this partial u partial x and partial u partial x, the gradient of displacement. We separated this term in two terms equal to 1/2 partial u partial x plus 1/2 partial u partial x. Obviously, it is a identity. And then we add one extra term here, 1/2 partial u partial x transpose. And then after this, we should subtract this term with the same term, because we cannot modify the term okay, by a non-zero value. So we add one term and then we subtract the same term, such that we are adding 0 here, okay? The equality won't change. But now we can rewrite this term as this term plus this term here, and then this term as this term plus minus this term here. So finally, partial u partial x equal to 1/2 this one and 1/2 this one. And then this is the string, this is the rotation. Before, not so many your attention have been drawn to the rotation part, because as a engineer, civil engineer, we concentrate on the deformation of the beam of column, something like this. So we concentrate on the beam, on the string, but we somewhat we get the importance of rotation. But it is okay. Why? Because in the classical theory of beam of the mechanical material, we assume that the rotation is very small, so this term can be negated. Okay. So we concentrate on the string tensor here, okay, and then we write 1/2 here, okay, here, like this. This one move to here. We have this relation, and then this one equal to this one equal to this one. This is a transpose. Let me show you. This one equal this one equal this one. Why they are the relation of transpose? See, partial u partial x1, partial u1 partial x1, partial u1 partial x2, but here is partial u2 partial x1. But this is partial u1 partial x1. So we take this term to here. This is the transpose. Okay, and this term take it to here. Okay, so we have the transpose, and then we sum it up together. We have 1 partial u partial x1, 2 partial u2 partial x1. So we have 2 partial u1 partial x1 cancel out with 2, and then we get this one. Okay. In the same way, we can have the shear component. Okay, like this. We can also write it as a component form. Epsilon 1,1 equal to this one. Epsilon 1,2 equal to this one. Epsilon 2,1 equal this one. Epsilon 2,2 equal this one. And then these four components can be rewritten as the indicial form. absolute ij equal to 1/2 partial ui partial xj and partial uj partial xi. We will come back to this notation later. Before we explain it, the mathematical rule of this term, we first give some physical meaning about the gradient relation here. What is the physical meaning of this relation? Okay, the x vector can be thought as a material line. Okay, and then du. What is the du? Du is the change of the displacement field of this material line. Okay, see, you have a material line, and then the material line will be deformed. Okay, and then in the deformation we have the displacement, so we have the change of the displacement like this. Okay, this is the basically the physical meaning of this relation. Let us look at the detail here. For example, we have a beam. We just randomly take one material line, AB, okay, AB, and between A point and B point, point B and point A, we have infinitely many material points, set across this line. So this is a material line here. We denote it as dx vector, okay? We call it the material line. And this material line will be deformed. So point A and point B will have displacements. But the displacement won't be equal zero, won't be the same. See, we have this material line bigger here. See, point A and point B will have different direction of displacement. Okay, this is UB, this is UA. So since the displacement at these 2 points are different, so we have non-zero du. So what is du? Du is UB minus UA, means that the displacement at point B and the displacement at point A are different. So they have a difference between these displacements. So this is du. And then how to compute du? Here is the mathematical relation. We have dx, and then we time it to the multiplied it to the displacement gradient, and then we get du. Okay, understand? For example, we have a material line here. It is in an inclined direction. So we have a horizontal component, a vertical component. Horizontal component is dx1, horizontal component. Horizontal component. Here, horizontal component, vertical component. See, this is a material line, but this is inclined. So we have the horizontal component and vertical component. Horizontal component is dx1. Vertical component is dx2, like this. Once we get this, we time this to the, multiply this to the displacement gradient vector, and then we'll get du vector right away. Understand? What is du vector? Du vector is the difference between the displacement of point A, point B and point A. Okay? This is the geometrical meaning of this mathematical relation. Okay? Let us talk about the index notation. Before we do this, we talk about the more general case, where three-dimensional case. We have epsilon ij's, epsilon 1, 1, epsilon 1, 2, epsilon 1, 3. Then we have the same in this whole expression. Okay, now, if we put r equal 1, j equal 1, what happened? r equal 1, j equal 1, we have epsilon 1, 1. 1, 1, 1, 1, 1, 1, 1, 1. So this one equal to this one, so this 1/2 can be cancelled out. We get this one. So as a result, begin from this index rotation, we get epsilon 1 equal to partial u1 partial x1. See? So it means that this index rotation can be a generalization of this expression. More, this index rotation can be used to get the shear component. For example, we said I equal 1, j equal 2, then 1, 2, 2, 1, like here. So 1, 2, 2, 1, like here. So epsilon 1, 2 equal to 1 half partial u1 partial x2 partial u2 partial x1. So perfectly. From this index rotation, we get the Lhamo string and the shear string at the same time. Okay. So this index rotation is a very convenient expression. Now we want to give you a what? Interpretation of the string component, the Lhamo string and the shear string. I think you had learned these components before, but I just want to give you a review here. Okay, what is the meaning of epsilon 1 equal to partial u1 partial x1? Let us start from a material line in the horizontal direction. We have a material line like this. And then, see, we have a horizontal material line. Huh? This point will move. This point will move. Okay, this point move here. This point move here. So we have a longer material line. Okay, this one connect here. So from AB, we deform it to A prime B prime. This is the material line after the deformation. This is the material line before the deformation, okay? So it becomes longer. So we want to compute the difference of the length of this material line with this. Let us start here. The x1 equal to BA, equal to x1b minus x1a. x1b is the horizontal coordinate of point B. x1a is the horizontal coordinate of point A. And then they subtract to each other to get the x1. Now, the y1 equal to y1b minus y1a. y1b minus y1a. But the y1b is the horizontal coordinate of point B prime is like this, equal to x1b plus u1b. What do you mean? Here, y1a, y1b is the position here, is here. And then equal to x1b times this displacement. Okay, so y1b equal to x1b times the displacement. In the same way, y1a equal to x1a minus u1a. Okay, now this one here, this one here. Okay, and then this is just the x1, this the u1. Okay, so we can put this one into the definition of the Lhamo string. Definition of the Lhamo string is the difference of the material length, okay, divided by the original material length. Okay, so the y1 minus the x1 equal to u1 here, right, time divided by the original material length. So what is the physical meaning of the Lhamo string? It is the ratio of the displacement difference to the what? To the original material length. Okay, this one times this one. Okay, so we have epsilon 1 equal to this one, and then we write like this. Okay, because in a more formal notation, we shouldn't use the total differentiation here. We use the partial differentiation here. Okay, so we replace this one by this one. This is the physical meaning of this term. How about the shear component? See, shear component have two terms. Okay, we want to expand this term only because the meaning of this term and this term are similar. So we focus on this term. Here we have partial u1 partial x1, but this partial u2 partial x1. They are different. Partial u1 partial x1, partial u2 x1. They are different. Okay, what do you mean? See here, we have dx1, we have the material line, dx1. Now we have the displacement not in the horizontal direction, is in vertical direction, u2. Vertical direction. Okay, u1 in the horizontal direction, u2 in the vertical direction. Understand? Once again, partial x1 is dx1, is the horizontal material line. But point A can be deformed in the horizontal direction and the vertical direction. If you deform it in the horizontal direction, we have this. But now if we deform in the vertical direction, we have this. Okay? And then this will give you the shear strength. Let us look at the picture here. We have the material line like this. Okay? Now point A deformed in the vertical direction, point B deformed in the vertical direction too. Understand? So we have U2A and U2B. At point B we deform like this, point A deform like this. Okay? So because the two vertical components, the two vertical displacements are different, such that so in this way the shear strength will be generated. Okay, so U2B not equal to U2A, so the material line will become a inclined material line, not in the horizontal direction. So we have a horizontal material line, one is deformed more, one deformed a little bit, so the material line will become inclined. Understand? Again, we have material line, one deform a little bit, one deform a lot. So the material line become an inclined material line. This one. Okay, so this is the original material line. This is the material line after the deformation. Okay, so we want to calculate the inclined angle theta here. Okay, now we want to remind you tangent theta equal to this one times this one divided by this one divided by this one. Tangent theta equal to du2 divided by dx1. Let us look at the picture here. This is u2b, this is u2a. So u2b minus u2a equal to dy2, also equal to u2. So du2, this is du2, okay? This section, the two section du2 times dx1 equal to theta. Okay, so we have the what? We have the relation here, tangent theta, but theta is very small, so we can approximate tangent theta by theta. Why theta is very small? Because in the classical theory of elasticity of beam or column, we usually assume that the deformations are very small, so the shear strength will not be very large. So in this way, theta is very small. Okay, let us look at the picture, the global picture of this material line. See, we have a material line here, just like this, AB, okay? It have a original horizontal coordinate, x1a. This is horizontal coordinate, x1b in the horizontal direction. And then this is the x2a. See here, horizontal coordinate, vertical coordinate, like this. But this point will move upward, have a displacement. So this is the vertical coordinate after the deformation, right? Likewise, point B, you have a horizontal coordinate and vertical coordinate like this, x1b, x2b. It moves a little bit upward to point B. We have a deformed material line here, like this one. Okay? And then this is the original x2b and then u2b, so we have y2b. Okay? Let us look at the relation here. Just like this. This one is this one. This one is this one. Okay? Now we do a little bit calculation. dy2 equal y2b minus y2a. dy2 equal to this one minus this one is dy2. Okay? And then we put this one into this one into this. But here, x2b equal to x2a can be cancelled out. Why? Why xb equal to x2a? See? x2a here, x2b here. So this is a horizontal material line. So x2a equal to x2b. So they can be cancelled out here. So we have this one minus this one. So dy2 equal to dx2. Okay? No matter how, we understand that the inclined angle is equal to du2 divided by dx1, like this. So this one, we divide this one into this partial u2 partial x1. So this is theta. Okay? And then so we have this angle, but also we have this angle called the phi angle. Okay? So we can have similar interpretation of this angle too, but we just skip it. We don't want to talk about too many details. Okay, they are similar. So in the same way, shear strain is equal to 1/2 theta plus phi, theta plus phi, and theta equal to this one, phi equal to this one. This is the interpretation of the shear strain.